YouTube, this is a continuation of my last video in which we're going to reconfront permutations, or at least the number of ways that exist to rearrange a set of objects, okay? But in this video, what we're going to do is we're going to confront situations in which we're not rearranging all of the objects that are being considered, but maybe only just a certain number of those objects at a time, okay? So we'll refer to this as a permutation, and recall that permutation is a situation in what we mean order matters, okay? Order matters when we talk about permutations. But maybe we have n total objects, and what we want to do is only rearrange r of them at a time. And you'll notice here I say that there are times in math in which we want to reorder or permutate, talk about a permutation here. Reorder a set of n objects. However, we only care to reorder a certain amount of them at a given time. And what we're going to do is we're going to say that if n represents the total number of objects that we have, R is going to represent the number of those objects that we want to rearrange, okay? So the examples that we went through in the last video, I've kind of repasted that screenshot down here. But we're going to work through them again just really quickly using this definition of a permutation. But we say that the number of permutations of R objects taken from a group of n distinct objects is denoted by n, these little subscripts here, is say n permute R at a time, okay? Where n, let's write this down, is the total number of objects, okay? And then R is going to represent the number of objects being rearranged, being reordered, okay? So the idea here is this: if we were to rearrange all n objects, we would just say that it's n factorial using the pattern that we discovered in the last video. But in this case, we say that if I have n total objects and I only want to rearrange r of them at a time, what we arrive at is this definition right here that says if you have n total objects and you want to rearrange only r of them at a time, what we get is n factorial over n minus r factorial, okay? And this is very much the case in all instances, all right? So what I want to do is I want to use this definition of permutations in order to validate our results in parts B and D that we did in the last video. And then we'll just show our work as well as use a calculator to verify our results. So in the last instance, we said consider the following. We had 12 skiers, so there are 12 total objects here. And they're competing in the final round of this Olympic competition. It says, in how many different ways can the skiers finish the competition? Well, remember, if we have 10 total objects and we wanted to rearrange all 12 at a time, we could just say, well, then it's 12 factorial. But in the instance where we said, in how many ways can 3 of the skiers finish first, second, and third to win the gold, silver, and bronze, order matters here, okay? So we are talking about a permutation, and we said using the fundamental counting principle, we could say, well, 12 people could finish first, but then there are only 11 people that could come in second, and then 10 people to choose from to finish third. What I want to do is I want to write this in other words. We say having 12 total objects, but the only ones that I want to rearrange are 3 of those, and those would be our gold, silver, and bronze finishers. So according to this definition, we would say that n is the total number of objects, r is the number that we're rearranging at a time, and we would write this as the total number of ways of doing this as 12 permuting 3 at a time. And that's how you would read this. I have 12 things, I want to rearrange only 3 at a time. So knowing n and knowing r and using our definition of permutations here, we say that it's n factorial over n minus r factorial. So in this case, we get 12 factorial over, in parentheses, 12 minus 3 factorial. So we're going to simplify this here, and I'll talk about how we easily simplify stuff of this nature, things of this nature, but we get 12 factorial over 9 factorial. Now, what we could do is we could write all of this out. Seriously, we could write 12 times 11 times 10 times 9 times 8 all the way down to 1, and that would be all over 9 times 8 times 7 times 6 times 5, and all the way down. What I'm going to point out here is this: the easier way to kind of represent simplifying this would be 12 times 11 times 10 times, and I'm going to write 9 factorial. And the reason why is because in the basement here, in the denominator, we also have a 9 factorial. And what I know is this: anything divided by itself is going to cancel out. So in other words, this 9 factorial in the basement, this denominator is 9 times 8 times 7 times 6 times 5 all the way down to 1. That would cancel out with 9 times 8 times 7 times 6 times 5 all the way down to 1 on top. And what we get left with is essentially this real substance right here, which I want to kind of point this out here, is the same thing we would have gotten had we used the fundamental counting principle to begin with. So really what we get is 12 times 11 times 10. So we get 12 times 11 times 10. In this instance, that's 1320. Now, I don't use this for permutations, ever, I guess. But I do not see a permutations option on the iMac or Apple calendar here. But most calculators, they'll have a permutation option. And the way you would evaluate something on that calculator is that you would actually have to type in, 12, and then you'll find an option that says, there's like an option maybe in a probability menu where you find NPR, and then you'll hit that, and then it'll say, 12. And then on your calculator screen it says NPR, and then you type in, you would type in how many you want to rearrange. And what it'll do is it'll kick out this value for you here. So again, in how many ways, let's say we have 10 golfers competing in a high school tournament, in how many ways could we rearrange all of them? Well, the fundamental counting principle will just tell us that there are 10 factorial ways to do it. But if I said in how many ways, if I have 10 total golfers, so our N would be 10, and I wanted to rearrange 4 of them, how many ways could they finish first, second, third, fourth? Order matters here, so we're talking about a permutation, and we want to rearrange 4 of them. So again, we say 10 permuting 4 at a time. I've got 10 total golfers. I want to rearrange 4 at a time. This would be 10 factorial over now n minus r, so 10 minus 4 factorial. In other words, we get 10 factorial over 6 factorial, and rewriting this, again, it is most convenient to say, well, this is 10 times 9 times 8 times 7 times, and we'll just call this 6 factorial, since we can get that 6 factorial to kick out here. And really what you see is this, the same thing we would have gotten had we used the fundamental counting principle. 10 ways to finish first, 9 people could finish second, 8 people could finish third, and 7 people could finish last. So we say 10 times 9 times 8 times 7, and we get this 50-40 value here. So what I've done is I've kind of built in a few special instances up here, 2 of them being special at least, and the last one not. But let's talk about this. If I said, let's find the following permutations in general. In this instance here, there are 3 total objects is our n value here. Okay, 3 total objects, and I want to rearrange 3. So if I said, well, if I've got 3 objects and I want to rearrange all 3, I hope you can see that that would be just really 3 factorial, because you are rearranging all of the objects. But in terms of our formula, why does this still work? What you get is this. You'd say, well, n is 3, so we get 3 factorial, n factorial, and this would be over n minus r factorial, so 3 minus 3 factorial, which this simplifies into 3 factorial over 0 factorial. And remembering, by definition, we say that 0 factorial is always equal to 1. This really simplifies into 3 factorial over 1, which comes out to be 3 factorial, which in this case, of course, is 3 times 2 times 1 is 6. So if you ever write n permuting r at a time, this would be the same thing as really just saying that many things factorial, because you are rearranging all 3 of those objects if there are 3 objects. So let's see, 5 permuting 2. If I had 5 total objects and I wanted to rearrange 2 at a time, how many ways could this happen? So let's go ahead and write out what we have. We have n factorial over n minus r factorial, which simplifies. We get 5 factorial. This would be over 3 factorial. And writing this out, we'd say on top we should write this as 5 times 4 times 3 times 2 times 1, which is really 3 factorial over 3 factorial. And our factorials cancel out here. So really we get 5 times 4, which is 20. And again, just consider this. Fundamental counting principle would say if I have 2 things I'm rearranging out of 5 total things, there are 5 ways I could choose something for the first spot, 4 ways to choose something for the second spot. It's the same thing you're getting with this expression that we keep evaluating. So in this last instance here, this is kind of a special instance. I'm going to drag this down here. What if I had 4 total things? There are 4 people in a room, and I say, okay, how many ways exist to rearrange? None of them. Seriously, consider this situation. How many ways exist to rearrange none of them? So now that you've considered this, hopefully, let's rewrite out our formula here. We say 4 factorial over 4 minus 0 factorial. This would simplify into 4 factorial over 4 factorial, and we would just get something that cancels out completely, and we would say that this just becomes 1. So consider this. If you had 4 different things to choose from, say 4 different people, and I said rearrange none of them, how many ways could you rearrange none of them? There's only one way to do it, and that way is to not touch anybody. Just leave them the way they are. So it makes reasonable sense that when you have n permute 0, anytime you have n permute 0, you're always just going to get 1. But the reason also is because when you plug it into this expression, you're going to get something divided by itself. Cheers.